Hello guys, and welcome once more to this new video on my YouTube channel. So in this video we are going to be solving the West mock. Actually we are going to be solving the West mock, that's the advanced level for mathematics paper 2 actually. So we are going to be solving question 9. Actually this question was on numerical functions. Actually the question reads: a numerical function f of real variable x is defined by f of x equals 2x plus 3 plus ln of x plus 1 divided by x minus 1. A. Determine the domain of definition df of f. B. Calculate the limits at the bounds of the domain. C. Evaluate the limit as x tends to plus or minus infinity of f of x minus 2x plus 3. Hence, state all the asymptotes of the curve CF of f. D. Show that f prime of x equals 2x squared minus 4 divided by x squared minus 1 and construct the table of variation of f. E. Sketch the graph of y equals f of x, showing clearly all the asymptotes and the behavior of the curve as it approaches the asymptotes. And F. Hence, find the coordinates of the center of symmetry of the curve. Let's actually move into the solution of this question actually. So we are given a numerical function f of real variable x, which is defined actually by f of x equals 2x plus 3 plus ln of x plus 1 divided by x minus 1 actually. So the question asks us to determine the domain of definition actually of f, that is df actually of that's the domain of definition of our numerical function f. So we know that actually, okay, for this function f of x to exist, actually what is inside the link function, that is x plus 1 divided by x minus 1, must be strictly greater than 0. That is x plus 1 divided by x minus 1 must be strictly greater than 0 actually. And also the denominator, that is x minus 1, must be different from 0 actually. So in the first place, let us first of all solve this inequality, okay, and see and find the values of x actually which satisfies this inequality actually. Yes. So what are we going to do? Simply we can use actually our normal line actually, that we can determine actually, we can solve the values of x, okay, we can determine the values of x, okay, which satisfy these inequalities, this inequality actually, by coming out with this normal line actually. So we have the roots -1 and 1 actually. How do we obtain actually these roots? By simply, okay, putting the numerator to be equal to 0, that is x plus 1 to be equal to 0, we obtain the first root, which is actually -1, and we do the same thing for the denominator, that is x minus 1, okay, equals 0, and we obtain the second root, which is actually 1 actually. Yes. So what are we going to do here actually? The thing we are trying to figure out is actually to look for the signs, okay, in the interval negative infinity, -1. We look the sign in the interval -1, 1, that we look the sign of x plus 1 divided by x minus 1, okay, in those intervals, that's the interval negative infinity, -1. We look the sign of x plus 1 divided by x minus 1 in the interval -1, 1, and we look the sign of x plus 1 divided by x minus 1 in the interval 1 positive infinity. If once we do that, we obtain the signs, okay, for example, if in the interval negative infinity, -1, we obtain the sign, for example, to be positive, that's greater than 0, it means the value of x actually satisfies that inequality. And do the same thing, that is, if the sign, okay, of x plus 1 divided by x minus 1, okay, is positive, okay, in one of those intervals, it means that interval, okay, which sign is positive, okay, contains the values of x which satisfy actually this inequality. So what are we going to do is that I'm first of all going to let, okay, this left hand side be equal to g of x actually, that is, let the g of x be equal to what is on the left hand side, that is x plus 1 divided by x minus 1 actually. So we are going to test, okay, we are going to take any values, okay, in all of those intervals and test the sign of g of x actually. If it is positive, therefore that interval contains the values of x which actually satisfies this inequality. Good. So in the first place, let us take, okay, in the interval 1, in the interval negative infinity, -1. Let's say for example -2, okay. So if we do g of -2, what are we going to obtain? Everywhere we see x will be replaced with -2, we are going to obtain g of -2 to be equal to -2 plus 1 divided by -2 minus 1, we obtain 1/3 actually, which actually gives us what? A positive sign in the interval negative infinity, -1, okay, and which already corresponds actually to 1, that is, it implies, since it is positive, it implies that what? It implies the values of x, okay, this interval, okay, the values of x in this interval satisfy actually this inequality, okay, because we have greater than 0 here actually. We do the same thing by taking a number in between -1 and 1. Let us say for example 0. If you take 0, we do g of 0. Everywhere we see x will be 0, we are going to obtain 1 divided by -1, which gives us actually -1, and from which we can therefore come and put the sign of the sign in the interval -1, 1 to be negative. And since it is negative, it implies the values of x, okay, in the interval -1, 1 will not satisfy this inequality actually. Yes. So finally, we do the same thing for the interval 1 point infinity. Let us say for example 2. In that interval, we have g of 2. Everywhere we see x will be 2, we are going to obtain g of 2 to be equals to 2 plus 1 divided by 2 minus 1, which is actually 3. And since it is 3, it means in the interval 1 point infinity, we obtain a positive sign actually, for which we therefore conclude that in the interval 1 point infinity, okay, the values of x in those intervals actually satisfy this inequality. Yes, actually. So in the interval -infinity, -1, and the interval 1 point infinity, there are values of x actually which contains which satisfy actually this inequality actually. So therefore we can therefore write that it implies x, okay, the solution to this inequality is what? X less than -1, that is this region, union x greater than 1 actually, this region actually. Yes. So as I earlier said also, okay, this is the first condition, okay, for this function f of x to exist actually. But it's another condition which says that what? The denominator, that is x minus 1, must be different from 0 actually for this function, this integral function to exist in first place. That is, x minus 1 must be different from 0, which actually implies that what? X is different from 1 actually. Yes. So these are the two, the values of x actually, that is this, okay, and this, that the values of x, okay, for which that the values of x actually for which this function actually exists, and which gives us actually the domain of definition of f actually. So actually there is a methodology which you have to use here when coming out with the domain of definition of a function actually. Yes, for this case of course actually. Yes. So the next thing you need to do is actually to do the union between the two. You can clearly see that in the first part we have x less than -1 union x greater than 1, and the second one we have x less than 1. You can clearly say if you make the union between the two, this, okay, will still work because actually x is not equal to 1 actually. Yes. So this, okay, that is x less than -1 union x greater than 1, actually give us the final, okay, definition, okay, for the domain. That is the final domain of definition g of f, or numerical function f actually. Which you can therefore write that the domain of definition of f, that is g of f, of our numerical function f is actually equals to -infinity, -1 union 1 positive infinity. It's actually what is being asked for us to determine in the a part of the question actually. Okay, let's actually move into the b part of the question. The b part of the question will be asked to calculate the limit at the bounds of the domain. We obtain the domain of definition d of f for a numerical function f, okay, to be -infinity, -1 union 1 point infinity. So in this question we are simply going to calculate the limit, okay, at the bounds of this domain. That is, we are going to calculate the limit, okay, as x tends to -infinity of our numerical function f. We are going to calculate the limit as x tends to -1 from below of our numerical function f. We are going to calculate the limit as x tends to 1 from above of our numerical function f, and we are going to calculate the limit as x tends to positive infinity of our numerical function f actually. So let us in the first place calculate the limit, okay, of f of x as x tends to -infinity. So the limit of f of x as x tends to -infinity is going to be the limit of 2x plus 3 plus ln of x plus 1 divided by x minus 1 as x tends to -infinity actually. So replacing everywhere we see x with -infinity, we are going to have 2 times -infinity, then plus 3 plus ln of -infinity plus 1 divided by -infinity minus 1 actually. So we know that 2 times -infinity gives us -infinity, -infinity plus 3 gives us -infinity actually. So here we are going to have actually -infinity. And what about here? Negative in the numerator, that is -infinity plus 1 gives us -infinity. Then the denominator, -infinity minus 1 gives us -infinity. So here we are going to have -infinity divided by -infinity, and at the end we are going to obtain a ln of infinity divided by infinity here actually. And from here we cannot judge, okay, we cannot conclude actually good things here. Why? Because we don't know these two infinities. We don't know whether they are the same, or we don't know whether the one of them is, okay, is greater than the other. So we don't know it's infinity. We don't know its nature actually. So we cannot conclude something from here. That is, we can't conclude from here actually. So what then can we do in order for us to proceed? Simply, this limit, we are going to adjust it in such a way that we can easily get a value actually from it. That is, we are not going to pass through this way. What are we going to do actually? We are simply going to factor out x here where there's this lim function. We can factor out x in the numerator and factor out x also in the denominator, from which we can obtain something good. Let us do that and let us see what we are going to obtain actually from there. So factoring x in the numerator and the denominator, we are going to have the limit as x tends to negative infinity of 2x plus 3, then plus, I factor out x in the numerator here, we are going to have x times 1 plus 1 divided by x, then divided by x, that is factoring x in the denominator. We are going to have x times 1 minus 1 divided by x actually. We know that what, as x tends to negative infinity, 1 divided by x tends to 0 actually. So here, of course, the x are going to cancel. So as x tends to negative infinity, 1 divided by x tends to 0. So here we are going to be left with 1 divided by 1, and 1 divided by 1 gives us 1 actually. So here we are going to be left with ln of 1. Ln of 1 is 0. So actually we are going to be left with what? 2 times negative infinity, we or negative infinity, then plus 3, which is negative infinity, because negative infinity plus 3 it gives us still negative infinity, then plus ln of 1. Ln of 1 is 0, which gives us actually negative infinity. So negative infinity, is the value. So the limit of f of x as x tends to negative infinity is actually negative infinity. Yes. So let's then calculate the limit, of f of x as x tends to negative 1 actually from below actually. Yes. So doing that, it implies that the limit of f of x as x tends to negative infinity is going to be the limit, of 2x plus 3 plus ln of x plus 1 divided by x minus 1 as x tends to negative 1 from below. So substituting everywhere we see x with negative 1, we are going to obtain 2 times negative 1, then plus 3 plus ln of negative 1 plus 1 divided by negative 1 minus 1. So here we can place that what? In the numerator we are going to have negative 1 plus 1, which gives us 0. So in the denominator we are going to have negative 1 minus 1, which gives us actually negative 2. So here we are going to have 0 divided by negative 2 actually, which gives us what? Which gives 0. Take note, we are going to have 0 divided by something negative. So 0 divided by negative 2. So we are going to have 0 minus actually here. So ln of 0 minus gives us which gives us actually negative infinity. Take note. So here we are going to have, that is ln of 0 divided by negative 2, gives us actually negative infinity. Then we know that 2 times negative 1 gives us negative 2. Then negative 2 plus 3 gives us 1. So we are going to have 1, then plus minus infinity, which gives us actually what? Negative infinity actually. So calculating the limit, of f of x as x tends to 1 from above, we are going to have the limit, of f of x as x tends to 1 from above to be equal to the limit as x tends to 1 from above of 2x plus 3 plus ln of x plus 1 divided by x minus 1. So replacing everywhere we see x with 1, we are going to have 2 times 1, then plus 3 plus ln of, in the numerator we are going to have 1 plus 1 divided by, in the denominator we are going to have 1 minus 1. In the numerator we are going to have 2, then in the denominator we are going to have 1 minus 1, which gives us 0. So here we are going to have ln of 2, we are going to have ln of 2, then divided by, we are going to have ln of 2 divided by 0, which gives us what? Which gives actually, here we are going to have positive infinity actually, yes, because we are going to have ln of 2 divided by 0. Ln of 2 divided by 0 actually gives us positive infinity. So we are going to have positive infinity, then plus 3, we get positive infinity, then plus 2, because 2 times 1 gives us 2, then plus 2 gives us still positive infinity actually. So the limit of f of x as x tends to 1 from above gives actually positive infinity actually. Yes. Let us then calculate the limit, of f of x as x tends to positive infinity. So remember, we were to calculate the limit, at the bounds of the domain. So we have already calculated the limit of f of x as x tends to negative infinity. We have calculated the limit, of f of x as x tends to negative 1 from below. We have calculated the limit of f of x as x tends to 1 from above. And here we are then going to calculate the limit of f of x as x tends to positive infinity. So the limit of f of x as x tends to positive infinity is going to be equal to the limit of 2x plus 3 then plus ln of x plus 1 divided by x minus 1 as x tends to positive infinity actually. So what are we going to do is that we are going to factor out, okay, x, okay, so we are going to proceed the same way which we did for the limit of f of x at x tends to negative infinity. That is, we factor out x in the numerator here, and factor out x in the denominator here. Those x are going to cancel, so that we are going to be left with what, 1, okay, then plus 1 divided by x. Then here we are going to have 1 minus 1 divided by x actually. Yes, so doing that we are going to have what, and at the same time replacing, okay, everywhere we see x with infinity, we are going to have 2 times infinity then plus 3 plus ln of, as I told you, we factor out x actually. Those x are going to cancel, okay, we are going to be left with 1 plus 1 divided by x, but we replace x with infinity actually. Then divided by 1 minus 1 divided by x, divide 1 minus 1 divided by x, but x will replace it with infinity actually. So this, that is 1 divided by infinity, and 1 divided by infinity tends to 0 actually. That is 1 divided by infinity, okay, tends to 0, and 1 divided by infinity tends to 0 actually. Yes, so here we are going to be left with what, ln of 1 divided by 1, that is ln of 1 will be us 0, because ln of 1 is 0. So we are going to obtain what, 0 plus 3 will be all 3, then 3 plus infinity, because 2 times infinity gives us infinity, that is 3 plus infinity will give us infinity actually. Yes, so we can therefore conclude that the limit of f of x as x tends to positive infinity is actually equals to positive infinity actually. Yes, so we can therefore conclude that what, the limit of f of x as x tends to negative infinity is equals to negative infinity. The limit of f of x as x tends to positive infinity is equals to positive infinity. The limit of f of x as x tends to 1 from above is equals to positive infinity, and the limit of f of x as x tends to negative 1 from below is equals to negative infinity, which is actually what was being asked for us to determine actually in the B part of the question, that is to determine the limit at the bounds of the domain actually. Yes, so the C part of the question was asking us to evaluate the limit as x tends to plus or minus infinity of f of x minus 2x plus 3 actually. So doing that, we are going to obtain what, the limit of f of x minus 2x plus 3 as x tends to plus or minus infinity to be equals to what, to be equals to the limit at x tends to plus or minus infinity of replacing f of x with its value, that is 2x plus 3 then plus ln of open bracket x plus 1 divided by x minus 1 then minus this 2x plus 3 actually. We can clearly see that this 2x plus 3 is going to cancel with this one, that is both of them are going to cancel, so that we are going to be left with the limit as x tends to plus or minus infinity of ln of x plus 1 divided by x minus 1 actually. Yes, so factoring x in the numerator and in the denominator, we are going to obtain what, the limit, okay, as x tends to plus or minus infinity of ln of x then times 1 plus 1 then x times 1 plus 1 divided by x, okay, then divided by x times 1 minus 1 divided by x actually. Yes, so these two x are going to cancel, we are going to be left with what, this, okay, as x tends to plus or minus infinity, 1 divided by x tends to 0, so we are going to be left with what, the ln of 1 divided by 1, which actually what, the ln of 0, ln of 1 divided by 1, actually the ln of 1 is actually 0, because ln of 1 is 0 actually. Yes, so we can therefore conclude that hence limit as x tends to plus or minus infinity of f of x minus 2x plus 3 actually is equals to 0 actually. It was being asked for us to evaluate, okay, in the C part of the question actually. Yes. So actually in the we have been told that hence states, okay, all the asymptotes of the curve CF of f actually. Yes, so we know that what, we know that actually the limit at the bounds of the domain, that is the limit of f of x as x tends to negative infinity is equals to negative infinity. The limit of f of x as x tends to positive infinity is equals to positive infinity. The limit of f of x as x tends to 1, okay, from above is equals to positive infinity, and the limit of f of x as x tends to negative 1 from below is equals to negative infinity actually. Yes, we also know that what, the limit as x tends to plus or minus infinity of f of x minus 2x plus 3 is equals to 0. From here we can only come out with big conclusions here actually. What are those conclusions actually? Since, okay, take note about those two things. Since the limit of x tends to 1, okay, of f of x, okay, that the limit of f of x as x tends to 1, excuse me, is equals to infinity, okay, it implies 1 actually is a vertical asymptote actually to the curve cf. And also, since the limit of f of x as x tends to -1, okay, is equals to negative infinity, hence -1 is also a vertical asymptote. Take note. And also, since the limit of f of x minus 2x plus 3 as x tends to plus or minus infinity equals 0, it therefore implies that what 2x plus 3 is actually our oblique or slant asymptote actually. So from it you can therefore come with those conclusions, that is the line actually the line actually x equals 1 and x equals -1 are vertical asymptotes, okay, of the curve CF actually, to the curve CF actually, yes. And of course 2x plus 3, that is y equals to x plus 3, is an oblique asymptote, okay, to the curve CF actually, yes. So in the deeper of the question, we are being asked to show that, okay, f prime of x equals 2x squared minus 4 divided by x squared minus 1, and construct the table of variation of f actually, yes. So we know that what f of x equals what 2x plus 3 plus ln of x plus 1 divided by x minus 1 actually, yes. So we have to differentiate this, okay, we have to differentiate this function actually. So we know that f prime of x actually is going to be equals to what? We have first of all to differentiate this 2x, okay, differentiating 2x in the first place we are going to have 2, then plus differentiating 3 to a constant give us 0, then plus differentiating this actually. So in order for us to differentiate this function, we have to differentiate this term, and this term actually, yes. So that is how we are going to proceed in order for us to differentiate this function f of x actually. So doing that, we are going to obtain what? F prime of x to be equals to differentiating 2x, we are going to obtain 2, then differentiating the constant, we are going to obtain 0, then differentiating this ln of x plus 1 divided by x minus 1, we are going to obtain applying the quotient. Here we have to apply what? We have to, in order for us to differentiate, okay, this ln of x plus 1 divided by x minus 1, the thing we have to do here is that what? Differentiate what is inside actually, then divided by this interior term. I take it back. In order for us to differentiate ln of x plus 1 divided by x minus 1, we have to differentiate what is inside, okay, and then we divide it by this same term simply. So you know that in order for us to differentiate what is inside, you simply have to apply the quotient rule, which I have simply applied here actually, that is bu prime minus ub prime divided by b squared, where u is the term which is in the numerator and b is the term which is in the denominator actually. So applying the quotient rule to differentiate this, we are going to obtain what? X minus 1 then times 1 minus x plus 1 then times 1 divided by x v squared, that is x minus 1 squared, then divided by the same term as I said, that is since we are differentiating ln of x plus 1 divided by x minus 1, so divided by the same interior term which is x plus 1 divided by x minus 1 actually, yes. So further simplifying, we are going to obtain f prime of x to be equal to 2 plus x minus 1 then times 1 minus x plus 1 times 1 divided by x minus 1, okay, then x minus 1 times x plus 1 actually, yes. First simplifying, we are going to obtain what? 2 plus in the numerator, simplifying the numerator, that is x, okay, it's going to cancel with this x, then -1, okay, minus 1, this is actually -1, okay, -1 actually minus 1, this is actually -2 actually, then divided by this one is a difference of 2 squared. You can clearly see that difference of 2 squared. We are going to have the denominator x squared minus 1. So looking for the LCM, that is further simplifying this, we are going to obtain 2 times x squared minus 1, okay, that we simply look at the LCM here actually, then minus 2 divided by x squared minus 1 actually, for which if you simplify furthermore, we are going to obtain 2x squared actually, that is 2 times x squared equals to x squared, then 2 times -1 equals -2, then -2 minus 2 gives us -4, then divided by x squared minus 1. This was actually what was being asked for us actually to show, that is to prove actually in the D part of the question actually, yes. So let us move then forward, okay, let us therefore construct actually the table of variation of f actually. So a table of variation consists of the domain of definition, consists of f prime of x and f of x. So where f prime of x actually, we are going to obtain the signs, the different signs, okay, in the different intervals, and from these signs we are going to okay, observe the behavior actually of our function f of x, okay, in those given intervals actually, yes. So our domain of definition was simply negative infinity, -1 union 1 positive infinity, okay, when -1 and 1 are not actually included actually into our domain of definition. take note actually. That's why I said I shaded this region here, that is in between -1 and 1 actually is not included into our domain of definition actually. Yes, so we have to know that what these values of x also, we have also to consider a very important aspect, okay, before proceed, which is actually what we have to check whether there is a turning point or not actually. So to do that, we have to consider this, okay, what the f prime of x, that is what we obtain, that is f prime of x, which is equal to 2x squared minus 4, then divided by x squared minus 1. We know that what at turning point actually f prime of x equals 0 actually, that is at turning point f prime of x equals 0. It actually implies that what 2x squared minus 4 divided by x squared minus 1 is going to be equal to 0, okay. Or furthermore, moving furthermore, that is for this, okay, for this left hand side to be equal to 0, actually the numerator must be obviously equal to 0, that is 2x squared minus 4 squared, okay, must be equal to 0. But further simplifying, we are going to obtain what x to be equal to plus or minus square root of 2 actually. It therefore implies that what this our function have a turning point. Take note, always check whether there is a turning point of not or not. In this case, we have clearly seen that what this turning point, and we have to represent it actually into our table of variation properly. Yes, so indicating those values of x, okay, into our table of variation, we are going to have negative square root of 2 and square root of 2 actually. Yes, so we have to obtain the corresponding images actually, okay, the corresponding, okay, the y value, y coordinates of our turning points actually, by simply what substituting the values of x, okay, that is obtain the values of the turning point into our function f of x actually. So if we do that for negative square root of 2, we are going to obtain the image, that is the value of f of negative square root of 2 to be actually equals to negative 1.59. Doing same for the square root of 2, that is f of square root of 2, we are going to obtain what 7.59 actually. Yes, so we calculated the limits, okay, at the bounds of the domain, so we have to take note of that. So this is where this limit actually comes into place, that is we have to represent those limits, okay, which we calculated into this table of variation. Actually observe how our graph is, how our curve is going to behave actually in the different intervals actually. Yes, so we calculated the limit of f of x, okay, as x tends to negative infinity, and we obtain what negative infinity. We calculated the limit of f of x as x tends to negative 1 from below, and we obtained negative infinity actually. Yes, since we obtained this, okay, we can therefore conclude that actually if we take, excuse me, this positive, okay, is as a result of what, if we take, okay, a value in between negative infinity and negative square root of 2 actually, we are going to observe that the sign of f prime of x in this interval, that is the interval negative infinity negative square root of 2, because positive, okay, on which you can therefore conclude that our function is going to be increasing, okay, in the interval negative infinity negative square root of 2 actually. Do the same thing, we look for a value in between in the interval in between negative square root of 2 and negative 1 actually. So and substitute it into f prime of x actually. Doing that, you're going to obtain what? You're going to obtain the sign of f prime of x to be equal to negative, that is to be negative actually. Yes, when you can therefore conclude our function actually is going to be decreasing in the interval negative square root of 2 negative 1 actually. Yes, we also calculated the limit of f of x at x tends to 1 from above and give us positive infinity. Okay, we calculated the limit of f of x as x tends to positive infinity, and we obtain positive infinity. Actually, if we take, okay, also a number, okay, in between 1 and square root of 2 actually, we are going to observe what, for example, you can take for example 1.1. okay, we are going to observe that the sign, okay, that if you take that number and put it here, we are going to observe that the sign of f prime of x is going to be actually negative actually. Yes, we can therefore conclude that our function is going to be decreasing in the interval 1 square root of 2. Of course, applying the same principle, that looking for a value in between negative square in between square root of 2 and positive infinity, okay, and substituting it inside f prime of x. For example, you can take for example 5, okay, and then substituting into f prime of x, you're going to obtain the sign of f prime of x to be positive actually, when we can therefore conclude that actually our function is going to be increasing in the interval square root of 2 positive infinity actually. So representing those arrows, that is those increasing and decreasing, okay, terms, you are going to obtain this, okay, as our table of variation actually. Yes, so let us therefore move into the last part of the question, into the last but not the least, okay, the E part of the question. where they are asked to sketch the graph of y equals f of x, showing clearly all the asymptotes and the behavior of the curve as it approaches the asymptote. Actually, yes. So doing that, okay, we have to come out with our xy plane. So you have to take note that actually this value which I have obtained here is as a result of what I had actually. So I observed that when I had my table of variation, I observed that my table of variation, I went to the values of x. I observed that my maximum value of x which I had was simply square root of 2. Yes, that is the values which I needed. That's the reason why you can clearly see that this on my xy plane, my maximum values of x is actually 2. Similarly, for the y values, I went to my table of variation. I saw that what is my maximum value which I had. We clearly obtained that it was 7.59 actually. It was the image of the turning point. That is the y coordinate of the turning point when x equals square root of 2. We obtain 7.59. So it is from those values that you can easily come out with your xy plane actually, as I did mine like this, because it's as a result of observing the different values of x and y that I could come out with this xy plane actually properly. Yes. So what are you going to represent actually? In the first place, as I explained earlier, that is from this table that I obtained the different values of x and y, and I could be able actually to put those values in this xy plane actually. Yes. So what next are we going to represent in this xy plane actually? We are going to represent the asymptotes actually. So in the first place, let us first of all represent the vertical asymptotes, that is x equals -1 and x equals 1 actually. So representing them, we are going to have these two lines with dotted lines actually. That is these lines, that is the line y, the line x, the line x equals to -1, and the line x equals 1 are the vertical asymptotes actually. Yes. So we have to represent also our vertical asymptote, our oblique asymptote, our oblique asymptote or slant asymptote actually, because we clearly proved that y equals 2x plus 3 was the oblique asymptote to the curve CF actually. Yes. So we have to represent this oblique asymptote in this xy plane. How then can we do that? Simply by coming out a small xy values. Yes. For example, we are going to have this small table where we are going to just put x values and y values and obtain some sets of values from which we can therefore represent on our xy plane. That is, for example, what happens when x equals 0? When x equals 0, substituting 0 here, we are going to have y equals 0 plus 3. Y is going to give us 3. And when y equals 0, what is x? X actually equals -3 divided by 2. So representing those 2 points, that's representing the point 0, 3 and -3 and -3 divided by 2, 0 on our xy plane. We are going to obtain those 2 points. That is this point actually the point -3 divided by 2, 0, and this one is actually 0, 3, on which we can therefore actually put our slant or oblique asymptote actually. Yes. So the next thing which we are going to do is actually to therefore indicate the turning points actually. We obtain our turning points, that is the coordinates of the turning point actually to be negative square root of 2, then -1.59, and square root of 2 and 7.59 actually. So representing those 2 points, that is this point is the point square root of 2, 7.59, which is this point here, and the point negative square root of 2, -1.59 is actually this second point here actually. So since we already have the turning points, that is those points, we can therefore actually come out with our smooth curve actually. Yes, that is, we can clearly say that our curve it comes like this, that is it moves, that is this first one. Let's first of all start with this first one. It comes from, that is from one, it does not touch the vertical asymptote, that is it moves from negative from positive infinity towards the turning point, and then move towards this slant asymptote actually, that is this vertical asymptote 1. That is, it comes from negative infinity, it does not touch this vertical asymptote, that is positive infinity, then it touches the turning point, and then it moves again towards positive infinity, trying to get towards actually our oblique asymptote. Yes, I saw. even if it is too far, but it was supposed to be much more closer actually. Yes. So then for this next curve actually representing it, that it comes from negative infinity, that it does not touch this slant axis from negative infinity, then it moves downward, that it curves, it touches, that it first of all touches the turning point, this turning point here, and then it swaps, okay, towards this vertical asymptote actually, that but it does not touch the vertical asymptote actually, so it just moves towards closer that vertical asymptote, which is actually -1 actually. Yes. So actually the input of question we have been asked to, we have been told that hence find the coordinate of the center of symmetry of the curve. So that coordinate is simply going to be this point, that is the midpoint, okay, is going to be the midpoint of the point of intersection between the slant asymptote and the vertical asymptote. That is this midpoint. You can clearly see that. I take it back. The coordinate, okay, of the center of symmetry of the curve is going to be what? The midpoint, okay, is going to be the midpoint of the point of intersection. That is the midpoint, which is this one, of the point of the intersection between the slant asymptote and the vertical asymptote actually. It's actually this point, from which you can therefore come out with the coordinate of this, because we obtain this point to be what? Actually 0, 3. Okay, so 0, 3 is actually the coordinate of the center of symmetry of our curve actually. Yes. So thank you very much, okay, for watching this video, okay, and happy new year, okay, merry Christmas to each and every one of you actually. So I would like you to, okay, to subscribe, okay, to YouTube channel, to share the content with your friends so they can also benefit from it, actually, to comment actually, okay, on the different aspects of the channel, okay, that if some things need to be ameliorated, to be changed actually, okay, to be modified, to be improved, you can, okay, write in the comment. You can write a comment actually and get a response properly actually. So thank you very much for watching, and remain tuned for a very next interesting video concerning the further mathematics, that is curve sketching. Of course, thank you very much and see you.